Zapping metals. Sounds pretty cool, right? Well, today we're diving deep into the science of laser ablation. We're going to explore how these incredibly powerful beams of light can shape the very stuff that builds, well, everything around us.
Think about steel, aluminum, copper. These are the absolute building blocks of our modern world. From the cars we drive and the bridges we cross, all the way down to the tiny electronics in our pockets. These metals are everywhere. They're the real workhorses of industry.
But here's the thing. How do you shape them with microscopic precision? When you need to cut or drill something with a level of detail that's just unimaginable, how do you even do that? The answer, and this is the cool part, isn't a physical tool. It's pure, concentrated energy.
And that's where we get to the power of light. Yep, we're talking about using lasers as this ultra-precise, totally invisible chisel.
So the key idea here is something called laser ablation. And it's actually pretty straightforward when you think about it. You basically fire a super-focused, really high-energy laser pulse at a material. The energy is so intense, it doesn't just melt the surface. Nope, it instantly vaporizes it. Poof, gone. It just cleanly removes a tiny, tiny layer of material.
So a good way to picture this is to think of a sculptor's chisel. Now shrink that thing down to a microscopic level and make it out of pure light. That's laser ablation in a nutshell. It's a way to carve with incredible detail without ever actually touching the material. Pretty amazing, right? Okay, but you can't just use any old laser pointer for this. Every single material has what's called an ablation threshold. Think of it as the magic number. It's the absolute minimum amount of laser energy, the technical term is fluence, that you need to hit it with to start that vaporization process. If you go below that number, you're pretty much just warming it up. Yeah, it's really just the minimum oomph. The laser needs to actually make its mark. And you can bet that knowing this exact number is super important for manufacturers. It's all about being precise and efficient.
But wait, it gets even cooler. There's this thing called the incubation effect. And what it means is that if you keep zapping the same spot over and over again with the laser, the material actually changes. It starts to build up these tiny little defects. And get this, that actually makes it easier to ablate on the next shot.
The jackhammer analogy is perfect for this, right? The first hit on a piece of concrete might just make a little dent. But if you keep hitting that exact same spot, the concrete weakens, and pretty soon you're breaking right through. It's the exact same idea here, just, on a ridiculously small scale.
All right, so now that we have the basics down, let's look at the actual experiment. Researchers wanted to put these ideas and our three main metals to the test. And the setup was actually really elegant and simple. First step, they got their samples of steel, aluminum, and copper. Step 2, they polished them up to create different levels of surface roughness, some really smooth, some kind of rough. Step 3, they zapped each one with a nanosecond pulsed laser. And finally, step 4, they pulled out a super powerful scanning electron microscope to get a good look at the crater they made. So simple, right? But the results, well, they were definitely surprising. And that brings us to what I'm calling a rough surprise, because this is where our intuition kind of gets turned on its head. It really shows you why doing the actual experiment is so important. So, let me ask you, just take a guess. What do you think is easier to ablate? A perfectly smooth, polished surface or a rough, unpolished one? Common sense might say the rough one, right? Seems like it would grab onto the light better. But is that what really happens? Nope. The answer, surprisingly, is the smooth surface. The data was super clear. The smoother the surface, the lower the ablation threshold, meaning it actually takes less energy to zap it away. How wild is that? So what's going on here? Well, think about a rough surface. It's got all these microscopic little peaks and valleys. And when the laser hits it, that surface acts like a really bad lens. It just scatters the light everywhere, defocuses the beam. So the energy gets spread out, it's less concentrated, and it just can't hit that critical ablation threshold as easily.
Okay, so we've got the whole surface roughness thing figured out. Now let's look at the metals themselves in a head-to-head competition. Which one is the toughest nut to crack with a laser?
To figure this out, we got to look at two main things. First, reflectivity, which is just a fancy way of saying how much light a metal bounces off, like a mirror. And second is binding energy, which is basically how tightly its atoms are holding hands. And as you can see, steel isn't very reflective. But look at copper. It bounces away almost all the light that hits it. And to top it off, its atoms are holding on for dear life with a really high binding energy. Okay,
So when you put all that together and look at how much energy it takes for one single laser shot, the results are just wow. Take a look at this. Steel needs about 7 joules per square centimeter, okay? Aluminum needs about 25. Makes sense. But copper, you're not reading that wrong. It needs 544. 544. That is just on another planet. It is so much tougher to ablate. So there it is. Copper is the undisputed heavyweight champion of toughness here. It reflects almost all the laser's energy, and the atoms are bonded so tightly that you need to hit it with just a ridiculous amount of power to even get it to notice.
Okay, so why should you care about any of this? Well, if you're in advanced manufacturing, this kind of information is pure gold. It means you can dial in the exact amount of energy you need for a job. No more, no less. That saves energy, it saves time, it saves a ton of money. But the biggest takeaway is this: there is no one-size-fits-all solution. Every single material needs its own special laser recipe.
And that really leaves us with a pretty cool final thought. You know, we're getting ridiculously good at engineering new materials, designing them right down to the atomic level. And as we keep doing that, mastering these invisible chisels of light is going to be absolutely crucial. It really makes you wonder, right? What kind of crazy new things will we be able to build when we can shape matter with this kind of pinpoint control? Something to think about. Thanks for tuning in.